All right, in this lecture, we're going to talk more about the equilibrium constant. And I want you to gain a feeling for an intuition for its magnitude and what that means about the concentrations of reactants and products relative to each other at equilibrium. We're also going to do some calculations using the equilibrium constant to figure out what equilibrium concentrations are for different species in a chemical reaction. So just to review, for a generic reaction, AA plus BB is in equilibrium with CC and DD. We can write the equilibrium constant K as the concentrations of the products raised to the powers of their stoichiometric coefficients. Okay. And it's just going to be the product of all of those products, multiplied by the concentrations of the reactants raised to the powers of their stoichiometric coefficients. So we have the product of those reactants concentrations raised to the powers of their stoichiometric coefficients. So you should be able to write an expression for K for any reaction. Now, I want us to think about this as just the concentration of products over reactants. And from that information, we can kind of develop a feeling for what the magnitude of K signifies. For example, if K is very large, if K is a lot bigger than 1, are there more reactants or products at equilibrium? Let's think about that question for a moment. If K is large, if it's much greater than 1, that means that the numerator is much larger than the denominator. Now, if the numerator is big, the numerator is products. So if the numerator is big, that means there are more products than reactants at equilibrium. Okay, because products are in the numerator. So a big K means we have more products than reactants at equilibrium, and we would say that the equilibrium lies to the right. The equilibrium lies towards the products. Conversely, if K is small, that is to say, if it's a lot less than 1, we have more reactants relative to products at equilibrium, and we would say that the equilibrium lies to the left towards reactants. Let's put this in a little table. So K is obviously never negative, okay? K is always going to be a positive number because we're dealing with concentration. You can't have negative concentrations. Now, if K is much, much smaller than 1, that means that the denominator is large, and the denominator is the reactants. So the concentration of the reactants at equilibrium would be higher than the products. So a K with a value much less than 1 would mean that the equilibrium lies to the left towards reactants. Conversely, if K is much greater than 1, we would have lots of numerator. So more products than reactants at equilibrium. If K is about equal to 1, that means that it's pretty balanced. You have, of course, it depends on the stoichiometry of the reaction, but you have kind of a decent amount of everything. We can say that both reactants and products are appreciable at equilibrium. So the magnitude of K gives you an idea of whether equilibrium lies towards reactants or towards products for a given reaction. Now, every reaction has its own unique K value, and the K is temperature dependent. And we can use the equilibrium constant K to calculate concentrations at equilibrium for all of the species in a reaction. So I want to do in this lecture a couple of examples where we put K to use for calculating equilibrium concentrations. Here's the first example. At 800 degrees Celsius, the K, the equilibrium constant, is 0.016 for the reaction where 2HI in the gas phase decomposes to H2 gas and I2 gas. Now, at equilibrium, the concentration of hydrogen gas is equal to the concentration of iodine gas, and both of them are 0.030 molar. From that information, we need to calculate the equilibrium concentration of HI, the reactant. So in this situation, we know the K value, We know the concentrations of the products. We don't know the concentration of the reactants. So the first step here is to write an expression for K based on the reaction. So looking at that reaction, my K is going to be equal to the concentration of the products raised to the powers of their stoichiometric coefficients. Now the reaction is balanced. The stoichiometric coefficients for both of these is 1, so they're raised to the power of 1. Over the concentration of the reactants, in this case we just have 1, raised to the power of its stoichiometric coefficient. So this would be the expression for K for that reaction. And I was told that K is equal to 0.016. Now, I can plug equilibrium concentrations into the K expression, and I know that at equilibrium, H2 and I2 are both 0.03 molar. So I can plug 0.030 molar in for H2 and I2. HI is what I want to figure out. Okay, so HI squared is going to be what I'm trying to figure out. And all of that is going to be equal to 0.016. So now I have one unknown, and I can do the algebra to solve for HI squared rather. So HI squared is going to be equal to 0.030 squared divided by 0.016. Okay, so you can simplify that, take the square root, and you will find that HI is equal to 0.24 molar. So this would be the equilibrium concentration of HI. All right, let's do another example. The equilibrium constant, K, is 0.11 for the reaction where 2-iodine monochloride gas decomposes to iodine gas and chlorine gas. Okay, that's a balanced chemical reaction. Using that information, can we calculate the equilibrium concentrations for all of the species in this reaction if the initial concentration of ICl is 0.10 molar? All right, so the initial concentration is not an equilibrium concentration. This is what we're starting with. So once again, let's write the expression for K for this reaction based on the stoichiometry of the reaction. So I have I2 raised to the power of 1, Cl2 raised to the power of 1 over ICl squared. Okay, you should be able to write a K expression for any reaction. We know that this K value is equal to 0.11 because the problem told us that the equilibrium constant is 0.11. So because we are only given an initial concentration here, it's useful to make an ice chart to kind of systemize our information. So in order to do that, I'm going to recopy the reaction, and underneath it, I'm going to make an ice chart. 2ICl, I'm just going to leave out the species for simplicity, are decomposing to I2 and Cl2. And underneath, I'm going to make rows with initial concentrations, change in concentration, and equilibrium concentrations. Now, I'm going to fill in this ice chart with what I know. And what I know is that I'm starting with 0.10 molar ICl. It is implied that I don't have any product to start out with. And I basically don't know anything else at this point. I have to make some guesses. So let's look at this. I'm going to change the color. I've basically used the blue to kind of fill in the information that I know. So I know that for every 2 moles of ICl that decompose, I'm going to get 1 mole of iodine and 1 mole of chlorine. So in my ice chart, I don't know what that change is going to be. So I'm going to say, okay, I'm going to be gaining some amount of iodine and some amount of chlorine, and they're going to be equal to each other, right? because of the molar ratio, they're going to be equal to each other. So I'm going to call both of them X. Now, for every amount X of iodine or chlorine that I'm gaining, I'm going to be losing some amount of ICl. Now, I have 2 moles of ICl that are being lost for every 1 mole of I2 or Cl2 that's gained. So I'm going to call that minus 2x. So basically, the coefficient of x that I'm sticking in my ice chart is equal to the coefficients of the stoichiometric coefficients in the reaction. So this enables me to come up with kind of algebraic expressions for the equilibrium concentrations. The equilibrium concentration of ICl would be 0.10 minus 2x. 0 plus x equals x, and 0 plus x equals x. So I have algebraic expressions for the equilibrium concentrations of each of the species in the reaction. Now, for K, you can only plug equilibrium concentrations into K, never initial concentrations. So that means I can take the equilibrium rho from my ice chart here and plug those concentrations into my expression for K. Now, let's take my K expression. I have it up here. K is equal to I2 times Cl2 over ICl squared. And plugging in my equilibrium concentrations, I have x times x, so that's x squared in the numerator, over 0.10 minus 2x squared. Okay, so I'm plugging in x and x into the numerator. X times x is x squared. And then the denominator, I'm plugging this expression in here, and then it gets squared because I have that exponent from the expression for k. Okay, so we can take a moment and put that down. I know what k is because I was told in the problem that the equilibrium concentration is 0.11. So this is going to be equal to 0.11. All right, now this is an equation that could be hard or easy to solve depending on the structure of it. But one thing that makes it a whole lot easier is recognizing that this is a perfect square, which is going to simplify the algebra quite a bit because I can take the square root of both sides. So the square root of 0.11 is going to be equal to the square root of x squared over 0.10 minus 2x squared. So that becomes x over 0.10 minus 2x. And now it becomes very easy to solve for x. X is equal to the square root of 0.11 times 0.10 minus 2x. You can distribute the square root of 0.11 through both of those terms on the right side and solve for x. X is equal to 0.020 if you isolate it on one side of the equation. Now, what is x? Going back to our ice chart, we can see that x is the concentrations of I2 and Cl2 at equilibrium. So I2 and Cl2 are both going to be equal to each other. And I have to remember this is in units of molar concentration. So this is molar. So the equilibrium concentration of I2 and Cl2 would be 0.020 molar. The equilibrium concentration of the reactant, iodine monochloride, is equal to the expression that we had in our ice chart. At equilibrium, it's 0.10 minus 2x. So 0.10 minus 2x is equal to 0.10 minus 2 times 0.020. So that should come out to be 0.060 molar. So these are the equilibrium concentrations for all three of the species in this reaction.